Hello and welcome to section 10, Structured Learning with Missing Values. Back to our COVID problem, we saw a number of methods to learn the structure from data. The question now is, what if we have missing values? So how is structured learning affected by missing values or hidden latent variables, which are variables without any observations? Say you have some variable that you know, for example, could be influential, or there's some probabilistic dependency with the other variables, but you have never measured it in your data set. So there are two components to structured learning. One is the score function, and there, because of marginalization and missing values, as we saw in the parameter learning, decomposability of the likelihood and hence related score functions is lost. Second is the search procedure, and this will be affected by the missing values, the calculations, the computation of the structure scores will be more complicated and time consuming, but also it will be more complex in the presence of a hidden variable, if there is any, and also by the uncertainty in the number of their values. In particular, if we're going to deal with hidden variables, we should detect three things. One is the need for introducing a hidden variable. Should we introduce it at all? Second is the position of this variable in the network. Should it be a top parent? Should it be a child? And third, the adequate number of values for the variable. Should it be a binary variable? Should it take 3 values, more, and so on? So both components will be more complicated. And now we're going to try to deal with them. So for the score function, consider the Bayesian score. We saw that the likelihood score easily gets overfeeded. Now we have the Bayesian score and the BIC score. The Bayesian score had this nice property of including the marginal likelihood, P of D, condition on G. So and we know that it was calculated using this integral when the data set was fully observed. But in the case of incomplete data, missing values or hidden variables, the likelihood is marginalized over unobserved variables. And this make it not decomposable, so we cannot easily calculate it. So how can we do it? How can we calculate this? I mean, this term is not that difficult. For example, if we have a uniform distribution, we can deal with it. But what about this one? Well, we can use the Laplace approximation. What is the Laplace approximation? Suppose f is a function that takes vector x and returns scalar fx. The Laplace approximation is the following. The integral of f of x is approximately equal to the value of f at x0, which is argmax log f of x, so it's the maximal where the log of x becomes maximum, times 2 pi to the power of dimension of c divided by 2 times the metric c, the determinant of it, to the power of minus 1 over 2. What is c? C is the negative of the Hessian matrix of log of fx, and it is evaluated at x0. So the entries of it, c, I, j, are calculated as follows. Okay. And the dimension is just the dimension of metric c, and the determinant is that this is just the determinant. You may say, like, why do we have logs here? There is another representation of this formula where instead of f, we use e to the power of f, and then we avoid the logs here. This representation is simpler for our use here. And this is the reason. We want to approximate the marginal likelihood. So we saw the integral. Let's define f of theta of g, as the term inside the integral. And we need the max log of this, which is basically the MAP, maximum a posteriori parameter estimation, because the maximum of the log of this is basically the max of this term. And we can add this normalization factor. Just if you check the denominator, it will be P of D and theta of G condition on G divided by D, which is basically P of theta of G conditioned on D and G, which is the posterior. Okay, now I can approximate the marginal likelihood. This is just the definition, integral of f, this term. And using the Laplace approximation, I will have the maximum of f appearing here and the remaining terms. Okay, so I can approximate log of the marginal likelihood, and we call it the Laplace score. So the Laplace score will be the log of the first term plus the log of the second term plus the log of these terms, which you will see that just the powers appear as a coefficient. Okay, so I have this. And what about C? How can I deal with that? Well, C is the negative Hessian matrix of the log of P of D condition on theta and G, this term, evaluated at the MAP. So this is basically, if you want to write it down, it will take this form. Now you see the left-hand side, this is just by definition, and it should be calculated at the MAP, the theta of MAP. And because the fact that P of D, it's data, it has like n instances, and it can be written under like conditions such as IID as the multiplication over P of each instance, and we're taking the log, so it will become the summation. So here you see the summation, and here just note that O of t is the observed data. Okay, and also note that here you see that the dimension of C is equal to the dimension of G, because the parameters are those that appear in the denominator, and they are basically the number of independent parameters, which is dimension of G. Now, to calculate the entries of C, we need the joint distribution over these variables given the observation, and this can be expensive if the variables are not in the same CPD. So in practice, score Laplace is not used. What can we do then? Well, we can try to approximate this term log of the determinant of C. And how can we do that? Well, C again is the negative Hessian matrix of the function log P of D theta G, and we saw that this can be written as the summation. And here is a little trick. We just write down C as the summation of CT, where CT is the Hessian of each of these terms. Okay? And therefore, we can do one thing. So the number of data instances, if they increase and go to infinity, then this term, 1 over n, so like the average of this can be approximated by the expectation of C of t, law of large numbers. So we can write down C as n times the average of this, which is approximately n times the expected value of C of t as n goes to infinity. Now I want to use this property that the determinant of some constant d times the matrix A is d to the power of dimension of A times the determinant. And we just saw that C will be approximately this term. If I take the determinant and I use this property, then n to the power of dimension of C of t, which is basically C, will be out of the determinant, and I will have this. Now if I take the log, then I will have log of n times dimension of C plus log of E of C of t. The whole trick that we did here was that to get this ECT out here and the log n here, because now as n goes to infinity, this doesn't grow with n. It's basically considered as a constant. So log of C will be basically log of n times the dimension of C. So as n goes to infinity, the Laplace score, which was this term, becomes this, can be approximated as follows, where we just replace log of determinant of C with log of n times dimension of C. And because n is approaching infinity, those terms without n in them, they will just be ignored, including this one and this one. This one has explicitly n, this one has implicitly. It's the data, which has the size of n. Indeed, it can be shown that as n approaches infinity, the Laplace score can be written as this term plus order 1, which are the other ones. Okay. So you may say that, well, this is quite familiar. I had the BIC score right here, the BIC, just that there we had dimension of G, the number of parameters, which we saw that it was basically dimension of C, but here we had MLE. So what should I do about that? Well, for a uniform parameter prior, then MLE and MAP will become the same, right? The main difference between the posterior and the likelihood was the effect of the priors. So then I can just have my BIC score written in this way. Okay? And also don't be concerned with this G. Because here theta is of G, of this structure G, putting G here or not doesn't really matter. It's implicit there. It means that it's of this structure G, and therefore we are assuming that the structure is G. So, well, I have my theorem. Assume a uniform parameter prior for all structures G. I'm putting it in gray. It's kind of implicit. Let n be the number of instances of a partially observed data set D. It wouldn't be surprising if it was fully observed. It is partially observed. So then I have, as n approaches infinity, the Laplace score can be written as the BIC score plus 0.1. Great. So for large number of instances, the log of the marginal likelihood is approximated by the Laplace score, and this is approximated by the BIC score. What does this imply? First of all, the trade-off between data fitting and model complexity that we saw in BIC, or the marginal likelihood, the B score, this is still preserved for partially observed data. This is great. So does this mean that we simply use this approximation or the BIC score? You may want to add that extra log of P of G to find the score of each structure and then find the highest one? Well, yes, we can just find the score of each structure, but that's infeasible if we have many structures, right? So, and we had a long discussion about this, like local search algorithms and all that. So if the number of structures are not too many, sure, but otherwise we need a search algorithm to do it. But the known algorithms such as hill climbing are much more computationally costly when we have missing data. So what should we do? Well, this brings us to the second part of this lecture, expectation maximization for structure learning. Recall that we can learn the parameters of a Bayesian network from partially observed data using EM. We had that in the parameter learning. Can we use it to learn the structure? The answer is yes. We can start from an initial network and iterate over some steps to learn the parameters of the network using EM, complete the data set, and update the structure. This is called the structural EM algorithm. And a remark that in each iteration of the structural EM, both structure and parameter learning are performed. So how does it work? Well, the structural EM algorithm is as follows. Consider an initial Bayesian network G0, the initial set of parameters theta 0, and the partially observed data set D. For step T from 1, 0, and so on, first we estimate the parameters theta of T prime. And how we do it, we use the EM for the structure GT, parameters theta T. Note that this theta T prime is different from this, and the data set D. Okay, then we construct the complete data set, and which here, note how we're denoting it. It's D of GT theta T prime. It means that it is based on the structure GT and the estimated parameters theta T prime. After that, we find GT plus 1, the new structure based on this data set. We just perform structure learning. We can use hill climbing, for example. The data set is complete. And at the end, we estimate the parameters using this updated structure and the data set. We learn the parameters for this structure. Now note the difference between T prime and T. T are the steps. T prime is the intermediate step. Okay. Now, the BIC score can improve in each step if the parameters are MAP. And here's the theorem. Look at the D, the data sets. This one is the original data with missing values. This is the complete data constructed from the structure G and the theta MAP at step T. What the theorem says is that the difference of G that we obtained, say GT plus 1, for example, from the GT that the data set was constructed from, this difference on the augmented data set, the complete data set, is less than or equal to the same difference on the real partially observed data set. So that means that if we have an improvement here, we definitely also have an improvement there. This is a real lower bound. So BIC can guarantee improvement over iterations if by, for example, hill climbing or any other local search, the GT plus 1 that we're choosing is really the one that has a higher score on this data set. So you saw that under some algorithms, we may force it, for example, to move to another neighboring structure, even though it wasn't earning higher. And you may be concerned with MAP, but again, like we saw that under some conditions, this is basically the same as MLE. Perfect. Let's see it in an example. The COVID mask problem, we want to learn it using this data set with missing values. We want to see the first iteration. Okay, so first I need to fill in these question marks. Remember from the EM in the parameter learning? Okay, so I start from these values of the parameters. How can I do that? Estimate theta 0 prime, and this is how we used to do it. We estimated the probability of the possible values for each of the question marks. So for example, the first instance has a question mark, a missing value. Mask can be either 0 or 1, and we calculate the probability of each of them given these parameter values. So it will be 0.7, 0.3, and so on. For the other missing values, we have 3 instances with missing values. Okay, so then I will get these, I will fill them in, and I will add the weights. The weights are exactly these numbers. And then I can calculate the parameters, the updated parameters. Remember the sufficient statistics. So I just count. Just this time I need to add the weights rather than just saying 1, 1. I put, for example, 0.4, 0.6, and so on. And I get my final value. So these are my updated parameters, the intermediate step. What should I do next? Well, now I will fill in my data set again with these updated values to obtain the structure. So how do I fill in the data set? Again, I will calculate the probability of each iteration, each instance based on these ones. And I will get the extended data set, and then I will find the next structure that I will move to. So here we have not many structures. I basically need to check only 2 because 2 of them will have the same score. So first one is just the structure without any links, and you can see that the BIC here is the likelihood that I'm calculating, and this is the penalty term. You see that the likelihood is basically the same as the formula we knew. Just here, these are n bars sufficient statistics. Okay, so if you plug in the values, this is the final value you will get. Same story with when we have a link m to c. Just this time we have, for example, c0 m0 divided by m0 because there's a link from m to c. And I can do the math and get the final value. So these will be the answers. If I change the direction from C to M, because of the score equivalence, I know that I will get the same answer. Okay, so we don't need to do this really. But okay, we just showed the calculations here. So anyways, I have the scores for the 3 structures, and we see that the one where there's no link, it had the high score. So I will go with that. That will be the end of my first step. No, I still have to calculate the parameters for that structure. And if I do that based on these instances, I can, and the augmented data, I can just calculate them this easily. Okay, so this will be the end of my first iteration. I have the values. I can go on with the second iteration. Again, calculate theta prime, go back to the original data set, try to augment it, extend it, the probability of each instance, they're calculated, extend the data set accordingly, and update the parameters. So we'll do that, and then I will get the updated values. We'll put it there. And now I should go back to the original data set, fill in these question marks with this updated parameter. So how to do that? Again, calculate the probability of each instance with these updated parameters, extend the data set accordingly, and now I have my data set, D of G1 with these theta prime, updated parameters. Now I can see if I should move to a new structure. And for that, again, I will check both of the structures without the link, with the link. These two are equal, minus 25.37, which is greater than minus 26. So I will choose this one, and note that the new score is higher than that of the last step. The last step was minus 25.46, and that's the idea we had, the theorem we had with the BIC score. Great, so I'm done. I will just stay at this structure. Well, almost. I just need to update my parameters as well, the final parameters, and that's very easy. I will just calculate them based on the table, and I'm done now. Okay, to summarize, the goal is to systematically find a P-map from data. What if the data includes missing values? How to do it then? And the idea was that we can use structural EM where iteratively in each step the missing values are predicted and the structure is updated based on completed data. Here is the diagram. We have the data set using EM parameter estimation and the initial parameter values. We got theta prime, and these were based on the structure. And then based on theta prime, we constructed the complete data set, and their structure and parameter learning were performed to get both the structure and update the parameters, and this process would go on. Thank you for your attention.